So we're going to start applying now what we've learned about the first and second laws, okay? And we're applying it to real systems. We're going to start with the internal combustion engine, okay? And that's something that everybody can relate to, very, very important, all right? So let's go over some basics of the operation of the internal combustion engine. Specifically, I guess this could be related to the four-stroke engine, but you can kind of similar ideas to the two-stroke. And let's think about this. Let's think, okay, so we got piston cylinder. Here we go. Here's our piston. Okay. And we got the cylinder, the top here, we got maybe something like that, and maybe something like this, okay? And what we have here is you typically have in a cylinder an intake valve and an exhaust valve, okay? Because inside your car, inside one of the pistons, what you're going to be doing is you're going to be bringing in air, putting a little fuel in it, compressing it, sparking it, creating that explosion, basically, right? Combustion, okay? And then that expands the piston, that pushes it down. And then what do you got to do? Well, you got all this combusted gases, you got to get rid of it. So you got to push it back out, and then you got to start the cycle again, okay? So you got the intake and the exhaust, you got the piston, of course, and the piston moves up and down, and it moves up to the top. We call this TDC, that stands for top dead center. And then the bottom of the stroke is called BDC for bottom dead center. Okay. The distance there between the top dead center and the bottom dead center is the stroke. Okay. Distance between top dead center and bottom dead center. And the volume difference, so this is the volume of the cylinder. The volume of the cylinder is going to be maximum when the piston's at the bottom dead center. So we'll say volume BDC. That's why it's at its maximum volume. Piston's at the bottom. Minus the volume when it's at its minimum, which is at the top dead center, okay, is equal to its, what we call its displacement volume. And displacement volume is something that you probably, if you've been around cars much, are familiar with, because sometimes they even like to put them on cars. If you look at some of the old Mustangs or maybe current ones, I'm sure I've seen it around different places, they'll put a little tag on there, 5.0. That's how many liters of displacement in the engine, okay? Or maybe it's a 5.3 or whatever. But if it's, you know, something like that, if it's 5 liters of displacement, that says that's a pretty good amount of power in that engine, okay? And remember, liters is volume, right? The more volume you've got between bottom dead center and top dead center there, and that's, of course, per cylinder. You probably have more than one, right? I don't know of a car that's just one cylinder. Not on the road today, at least. You probably have more than one. That combined volume of all the cylinders, okay, gives you the displacement volume, right? And we've learned, what do we learn? Work is equal to integral PDV, right? And volume change is very important to work, and work is what makes your car go. So the more volume, the better, right? So car companies say, let's put that little sticker or put that little emblem on our car, 5.0 or whatever, right? That says there's a lot of displacement volume, okay? And the car people go, yep, I understand that, because volume means power, okay? And that's what that is, okay? And they just put it in liters. People talk about it in liters. That's power. Volume is power. Okay? So that's some basics there that we're going to have. We're going to go over the basic four-stroke internal combustion engine. We're going to model it using something called the Otto cycle. But before we do that, I want to get into what we call the air standard assumptions. And these are the assumptions we're going to be doing whenever we model an internal combustion engine. Okay? We're going to model an internal combustion engine. We're going to use these assumptions. And they're going to be true whether we model it like we do today, which is the spark ignition engine, or when we do on Thursday, which is the diesel. Okay? Because the cycles are slightly different. Okay. So first thing is that in terms of assumptions we're going to make, is we're going to assume that we're dealing with air at all times, okay? And of course, we always like to assume air is an ideal gas, right? Of course. We're dealing with air, ideal gas. Now, is that exactly true? Well, mostly it's air. If you think about what happens inside your engine, it brings in a lot of air. There's not a lot of fuel. I mean, the air-fuel ratio inside the cylinder before you have the combustion, it's mostly air. By volume, by weight, it's mostly air. There's very little fuel, of course, right? We hope not, because you're doing that same process a lot. And so you don't want to have a lot of fuel in there. It's mostly air. But then after you combust, it's air and fuel is basically a chemical reaction. And that chemical reaction, that's not exactly air anymore, right? We know what comes out of our tailpipe is not exactly breathable air, right? It's not the same thing. So they're a little different, right? It's a little different, but it's close. It's close, it's good. We're going to assume everything is air, okay? So that's first thing. Second thing we're going to do to simplify as well is we're going to assume all the processes are internally reversible. Okay, internal reversibility. Basically, that means that we're going to assume there's not a lot of friction or not a lot of unrestrained expansion of gases on the inside. That's actually not that crazy, okay? I'm not saying it's totally reversible, by the way, because that would be crazy. I'm just saying internally reversible. You still have heat transfers and things like that, okay? But inside, it's reversible. So, you can get gas back into the tank. Oh, yeah, they can't do it like that, yeah. Okay, third thing is that combustion. Okay, when you've got air, you've got fuel, and at the right time, we put in a spark, right? We basically have a controlled explosion. We're going to say that that process, which is a chemical reaction process, right, which releases energy, right, it's a release of heat, right? We're basically going to say, when we say that happens, combustion is really just a heat in. It's really just a heat into the system. That kind of makes sense, right? I mean, when you have combustion, it's a lot of heat. It generates a lot of heat. We're going to pretend that that's just heat into the system. Okay? And then finally, what you have to do after you've done the combustion is you have to open up the exhaust valve and you've got to push out the exhausted gases, right? Well, we're going to assume that exhaust is really just heat out. Okay? So if we do those four assumptions, we can simplify and bring something that's manageable, but we don't lose, hopefully, too much in terms of real modeling of the system. Okay, that's the goal. We want to get as close as possible, but doable. And those assumptions are going to get us a lot of the way. One more thing I should mention before I get into the details of the Otto cycle is in this whole process, when we do the Otto cycle, we're going to basically assume a closed system. Okay? That's not really true, right? I mean, if you look at your engine cylinder, that's not a closed system. The intake valve opens, air comes in. The exhaust valve opens, the exhausted gases go out, right? It's not really a closed system. We're going to pretend it is. Okay, we're going to pretend it is. All right? So we're going to model this as a closed system. Okay? And the reason I bring that up now is that for a long time, you guys have now gotten so used to modeling control volumes, and you've gotten so used to saying, oh, I need to get my H's. I need to get my enthalpies. And now we go back to U's again. And now we go back to internal energy, because remember, when we're modeling a closed system, we use internal energy because there's no flow work across the boundary. Okay? So closed systems, we use U, not H. All right? So that's a little bit of a back to the beginning here. Okay. So I'm gonna go through the process of the Otto cycle here, and I got 4 boxes to go through each process. When I do it, I'm also going to describe the real cycle and the difference between the two. All right? The first part is what we call the compression stroke, and it's pretty much just like the real one. Okay? This is just like pretty close to what happens in your car. You got your cylinder, you got your piston, and what happens is that the piston rises and begins to compress what really would be an air-fuel ratio in here. Okay? What's really going on inside the cylinder is it's an air-fuel ratio. Okay? But let's just pretend that it's just air, because that's what we're going to do. Pretend it's air. And so this is really the compression stroke. We're going to assume, by the way, this is isentropic compression. Remember what that means? Constant entropy, right? But what that really means is it's going to give us some of those isentropic relation equations. And I forgive you if you don't remember them, okay? Because there's a bunch of them, all right? But they're in your equation sheet that you got on last week's test, okay? But there's a bunch of isentropic relations. Now, the good news is we're mainly only going to use one, okay? So it's not like you have to memorize all these different, no memorization, okay? But we are going to use an equation there that's going to help us, and I'll go through an example later. But for now, just say, okay, we're compressing air, right? We're just going to compress air in the compression stroke, and it's isentropic compression. Okay, yada, yada. All right. Number 2. Now that we have compressed the air, so now I want you to draw it with a smaller volume. We've got a smaller volume here, something like that. We've compressed it, okay? We are going to add heat, Q in. We're going to add heat. That's basically like what happens when you spark. When you have your spark plug activate, right, inside the cylinder, it just, boom, it creates that reaction, right, and that reaction gives off a whole lot of heat, right, boom. So that's what that is, basically. But here's the deal. We're going to assume that basically it's a heat addition at a constant volume. Basically what we're saying is that combustion occurs so quickly and gives us heat so fast, it's almost as if the piston stopped and it happened only when it stopped at its top. Okay? The reality is the piston's constantly going up and down, right? I mean, that thing is going down, up and down very quickly, right? Very quickly. Okay? So, you know, you've got a lot going on there. It's going very, very quick. Depends on your RPMs, right? It's going, so. By part, we're going to like freeze it. We're going to pretend it stopped. And that combustion happens pretty quick too. You want to see how fast combustion happens, you know, get some atomized fuel in some air together and light a match. Right? It happens pretty quick. So combustion, the speed of combustion is pretty fast. Okay? So it's not that crazy. All right? Okay, so we got that. That's step 2. Step 3, so that's the constant volume heat addition, Q in. All right, step 3. All right, this is what we call the power stroke.
So the two does not have a name?
Constant volume heat in. Constant volume heat in. That's why I drew constant volume and I have heat in. But yeah, you're right. I could write constant volume heat in.
Oh, so that is okay.
Sorry, yeah, it's not anything fancy.
Right.
Okay. The power stroke. This is where you get your power. This is the only part of a four-stroke engine that actually gives you power, that actually does what we want it to do, okay? And so what we have with the power stroke is you have an isentropic expansion. Now, once you've got that heat in, you've got that explosion, then what happens is that the piston goes down, you have expansion inside the cylinder, okay? Isentropic expansion, I'll write it down here. Okay? This is the only stroke in a four-stroke engine that gives you power, okay? The reason why you have four cylinders a lot in cars, because at least, but four is a nice number, is because if you have a four-stroke engine and you have four cylinders, you can time them so that one cylinder is always on the power stroke. Okay, you can time it that way, right? Because whenever you have any multiple cylinder engine, they're not running at the same phase. They're out of phase, right? One may be in the power stroke and one's in the exhaust or something else. Okay, so what you do when they design a car, four cylinders is a prime example, is that you have each one of them in a different stroke at the same time, so that you always have a power stroke. That means you're continually getting power from your engine. Okay, that's the point. Okay, that's why you see four cylinders a lot. Four makes sense if you have a four-stroke engine. Now you can do it with six too, and then you've got some different times where you might have more or less or whatever. They're all timed out differently as well. Okay, you know, you could have a little bit of a different phase on that. 8 is also good because when you got 8, you got 2 going at the same time, right? Okay. And you can have two-cylinder engines too. They're out there. There's not a lot of power.
Like I do in high school, doing a 3-cylinder.
A 3-cylinder? Yeah.
That was 4.
Yeah, you can do it. I mean, you can have them out of phase too, you know, and have them out, you know, and have, but yeah, I mean, you can have a 1-cylinder vehicle, but then only a quarter of the time are you getting power. So it's probably going to be a little jerky. Yeah, just one cylinder, you know, so it's hard, but it's much smoother. You know, 4 is a real smooth application. Now 3, you can do 3 if you do the right phasing as well to, you know, get pretty close. Okay, but the only time you really get power is the power stroke. It's isentropic expansion. Okay, the last thing, and that is here, and that is we have a constant volume. We draw a large volume here, and we'll say this is Q out, okay? And this is constant volume heat out. Oops, of course. Oh, there's 2 3s. Constant volume heat out, okay? So again, the assumption that we're making here, constant volume. Now, if you follow this along very carefully, it only looks like 2 strokes. I said it's a 4-stroke engine, and yet if you follow my diagram of an Otto cycle, it surely looks like 2 strokes. What happened? Well, that number 4 is actually 2 strokes, whereas 1 through 3 is also 2 strokes, okay? Because you have a compression stroke. 1 is a compression stroke, so that's a stroke. 2, that's not really a stroke at all, just a phase, yeah. 3 is a power stroke, so there's stroke number 2, right? And 4 is what they call constant volume heat out. But what really happens in a regular 4-stroke engine is that once you have the power stroke, you have to have a stroke to get rid of the combusted gases. That's stroke number 3. And then you have to have stroke number 4 to bring in new air. Okay? So really, step 4 here is 2 strokes out of the... It's kind of hidden, but it's really 2 strokes. Okay? 1 is a stroke, 3 is a stroke, and 4 is really 2. Okay? If you think about it. Okay? Now, you can do 2-stroke engines as well. Okay? 2-stroke engines, they just have a power stroke and an exhaust. Power, exhaust, power, exhaust, power, exhaust, power, exhaust. That's all they do, basically. Okay? And you get more power per weight out of a 2-stroke engine than you do a 4-stroke. Okay? You get more power per weight out of a 2-stroke than a 4-stroke. Why? Because half the time you're getting a power stroke. In my 4-stroke example, only 1/4 of the time are you getting a power stroke. But in a 2-stroke engine, half the time you're getting a power stroke. So you have a power stroke, and then you have exhaust, and basically your intake and exhaust happening at the same time. You you get rid of the combusted gases and intake the new stuff at the same time, and then you do a power stroke again. You can do them together. So, and that's what, and 2-stroke engines, when 2-stroke engines are things like weed whackers or weed eaters, whatever you want to call them, lawnmowers, things like that. A lot of gas-powered yard equipment, almost all of it, is probably 2-stroke engines. Okay? Why? Because you get more power per weight. Okay? So you get more power per weight. It's a lot simpler design, okay, to do a 2-stroke engine. A lot simpler. Okay? Well, then why don't we have cars? If we get more power per weight, why don't we have cars that have 2-stroke engines? So, not necessarily lower efficiency, but the problem is that you tend not to have a complete combustion when you do a 2-stroke, and that the process of a 4-stroke does a better job of completing the combustion process and essentially ends up being cleaner. Okay? I don't know how many gas-powered lawn equipment you've run, but have you noticed they have a lot of smoke in them? Push out a lot of smoke and stuff like that. Can you imagine your car's putting out that much smoke and junk, right? It's just not as clean a combustion. Yeah.
So why is it that you mix the oil with gas?
Yeah, you do mix the oil with the gas because that's part of the whole process. I mean, it's got to have it all in there. So yeah. Yeah, it's still, well, it does still inject it and things like that, but it's all kind of mixed together. It's definitely more mixed together than in a 4-stroke. So yeah. Oh yes, yeah, it's definitely smaller. You get more power per weight out of a 2-stroke, but not as good a combustion. So, by the way, there is a lot of research going on in 2-stroke engines in cars because we think, well, if we get more power per weight, maybe we can lower weight, we can get efficiencies better. There's a lot of things that could be better, but the problem is we've got to make sure we get that better combustion so we don't put out as much junk in the air and all that stuff. So, we got to do that. So,
depending on where the valves are, since like a 2-stroke engine,
yeah,
it's taking in air and like
putting it out at the same
putting it
time.
out at the same time. What if you have a possible problem with like some stuff put out coming back in?
Yeah, usually it's on different sides. That's usually how they do it. You have one side has the intake and one side has the exhaust in the same place. So usually that's not a problem. I mean, if you were in a real enclosed area, it probably would be. But, hopefully you're not operating power equipment in an enclosed area. So those gas-powered lawnmowers and things like that in a garage or something, that's probably bad. But yeah, I mean, I guess in theory that could be true, that you could have some exhaust, but generally they design them on different sides, and so usually that's, even the lawnmower, you've got, if you look at it, one side that's going to have the inside intake and one's going to have the exhaust, and so they kind of usually separate those two out. Okay, so this is, and by the way, in everything here, I want to make sure I'm clear, I'm modeling the spark ignition engine. Okay, this is for spark ignitions. The Otto cycle is for spark ignition engine, so I want to make sure that's clear. This is the ideal 4-stroke IC engine for spark ignition. Spark ignition. We're not talking about compression ignition, aka diesel.
No, we talked about that first.
Yeah, exactly. So we'll talk about it a little bit today, though, too. All right. By the way, let's take a look at this in terms of a PV diagram, too. Okay? Because, you know, we like to do that. And so here's what it would look like on a PV. You start out here, the highest volume, lowest pressure,
That's
right?
specific volume or regular volume.
Doesn't matter, because the same mass is the same the whole way. It's a constant mass inside. So whatever you'd like it to be. So so you've got low pressure, high volume. That's the beginning of the cycle. Then what do? We compress, right? That's the first part of the cycle. So it's an isentropic compression. It's going to look something like that. It's not a straight line. Okay, we're going to compress like that. All right. Then what are we going to do? We're going to have a constant volume heat addition. So constant volume means it's going to have to go straight up. Okay, heat addition to state 3. Then we're going to have another isentropic, this time an expansion, to state 4. And then we're going to have a constant volume heat out. Okay, so this is Q in. This is Q out. Okay, and these processes from 1 to 2 and 3 to 4 are isentropic. Okay. So, did anybody remember the definition of work as integral what? P to V, right? That's, I asked very little of memorization, but I want you to know work is integral P to V. So you should hopefully, with enough calculus knowledge, look at this and go, oh, I have a P versus V curve. So therefore the work is the area inside this thing, right? That's the work. That's the work. That's what I'm getting out of this thing. Making my car go, making the lawnmower turn, making the leaf blower blow, whatever. All right. Okay. Now, let's talk about efficiency. I'm going to spare you the details. If you want to go in the book and look at the details, it's not that hard, but I just don't want to spend the time on it. But the efficiency of the Otto cycle has a really interesting implication. Efficiency, remember, is what you get out divided by what you put in. Okay? In any car, that's pretty easy. I mean, the easiest measure is miles per gallon, right? I mean, think about that. Efficiency is miles per gallon. I want out of my car a lot of miles. I put in gallons. I don't want to put in a lot of gallons, but I have, right? So efficiency is what you get out by. Now gallons of fuel, we call that heat in, because if you burn the fuel, that's basically heat, right? So Q in is basically gallons of gas. Okay, that's just heat, right? So efficiency is work out miles basically divided by Q in gas, miles per gas, or whatever. Distance per gas. Okay? So you can easily show for any heat engine that's equal to 1 minus the Q out divided by the Q in. Okay, whatever. But here's the really interesting implication. It's equal to 1 minus 1 over R to the K minus 1. Okay, well, what does that mean? Well, K, remember K is just your specific heat ratio, which is 1.4 for air. Remember, we're using air assumptions, so okay, that's not that important. Okay? What's really interesting is R. R is the max volume divided by the min volume, okay? Which is better known as the compression ratio. Okay? And here's what that's implying. What we're saying is that if you have a large compression ratio, if you look at this carefully, what that implies is that you get more efficient vehicles. Okay? So if I want my car to give me the most miles per gallon, I want the largest compression ratio I can get. Okay? I want my engine to give me a large compression ratio. Basically, the difference, the division of the max volume divided by the min volume inside each cylinder, I want that number to be really, really big. Okay? Problem. The problem is that when I compress air-fuel ratio too much, it ignites. Yep. It's called auto ignition. Betterwise known to the general public as knocking. Okay? Your engine will begin to knock. Okay? If you compress that thing too much, it knocks. It basically what happens is it ignites before you want it to. You want to ignite when that spark plug goes, and that spark plug goes when you're at a minimum volume. Okay? But if it ignites too early, that puts a whole lot of pressure on those pistons. It hits it the wrong way. It's not designed for it. You know, all the assembly of the engine, connecting rods, things like that, get a way different amount of force that's not designed for it. And you can really be rough on your engine. Okay? So you don't want auto ignite. And it makes a lot of noise, too. So it's just rough on the engine. Very rough on the engine. Okay? So you don't want to auto ignite. Now, some cars, especially higher end cars, more expensive cars, run on higher compression ratios. But then you know what? You got to put in the good fuel. That's why they'll say, if you look at the owner's manual of some of the higher end vehicles, that you have to have premium fuel. Because one thing that we've done in cars to help keep this auto ignition from happening, we don't want the fuel to ignite too early. So what they do is they put extra octane in the fuel, okay? So when you go to the pump and you look at octane levels, you see 87, 89, 91, whatever, 93, right? You see different octane levels. All that is there for is to allow the vehicles to run at higher compression ratios and keep them from knocking, okay? So if you don't have a vehicle that requires higher fuels, getting higher fuels in there won't help it any. Okay? The only thing that a higher octane fuel will do is that it'll keep it from knocking on the higher compression ratios. Okay? And some cars have those. Typically they're more expensive because they know that people probably, are not going to, people buy a cheap car, they probably don't want to pay for expensive gas. Okay? That doesn't make a lot of sense. So they usually put them on the higher end cars, better compression ratios, more power, things like that. Okay? So don't put the expensive gas in if you don't need it. And only need it if your owner's manual says. And the only owner's manual says it is if they run higher compression ratios than normal, cars. All right? But that's good in some ways to run higher compression ratios because then you can get more power out. You can have more efficiency. Yeah.
I've had a shift in my truck. You said when you go to the higher
Yeah.
grams, you
Yeah.
have to run 91 in it.
Yeah. Yeah. Yeah, that's because they're running higher compression ratios. They've got something that's controlling that. Yeah, yeah, they're running higher compression ratios, and they're going to give you more power. It's going to give you more power, yeah, and keep that from happening. Okay, so that's why we have the higher octane fuels. Okay, now the other way around it is to just say, you know what? I like auto ignition. I don't want to have spark plugs.
Auto ignition is actually like
With
auto ignition, since it's all being compressed.
Yeah.
The spark plug, you got that point where the ignition starts from the auto ignition. Does the whole thing go off at once?
Yeah, typically it's all just right there.
So it's a lot quicker than spark plug, wouldn't it?
Oh, I don't know. A spark does it pretty quick too. The flame dynamics. I mean, there's people that study that kind of stuff. Yeah, there's people that study that kind of stuff. I don't know. I'm not sure. I don't know. I don't study wave and flame dynamics enough to give you a definitive answer on that, to say if it's how much faster or not. My mind would say it wouldn't be, but I don't know. But diesel, which doesn't have spark plugs, takes advantage of it and says, you know what, who needs spark plugs? We'll just design these things to run higher compression ratios, and we'll just let it go on its own. And we get more power. Hey, isn't that great? We get more power. All right? And diesel is really making a comeback, because you see things like the Volkswagen Jetta that's running diesel. It's a cleaner diesel now. We've learned how to get it a little bit cleaner in terms of the whole exhaust management process. And we've gotten more power per stroke because of higher compression ratios. That's why your big trucks and things are all diesel, because you get more power on it. Okay? Yeah.
Then why can't you have a gasoline engine with auto ignition on it? Even if there's a reason why, but just no one done it yet.
Oh, a gasoline engine with just running on straight gas? You could. You have to design it for that. And the thing about straight gasoline, it's actually more expensive to make it. There's more refining in straight gas. So you might as well just use the diesel, because why would you refine it more to add stuff to prevent auto ignition? That's what I'm saying. Like, diesel should be cheaper. Now you say, why is it cheap? Why is it more expensive? That's a whole nother economics, supply, demands, all this stuff. Greedy corporations, who knows, right? Yeah, there's a whole lot of other things going on there. Yeah. So, there's not much. There's some refining, obviously, to diesel, but it's not nearly as refined as regular gas. And so, it should be cheaper. And so, why would you add? That's the thing. That's really the thing. Is why would you add octane and things like that? Why would you refine the fuel just so that you can prevent auto ignition, but then you want it? That's why we just run on diesel. Yeah. So that's the main thing. But I remember diesel as a kid, and they were always loud. Diesel cars. We had a lot of diesel cars 30 years ago. 40 years ago. A lot of diesel cars. They were loud. The engines had to be bigger, heavier, things like that. A lot of engines have to be bigger and heavier because the explosions are less controlled, more rough, harder to, just much more wear and tear. So we made the cylinders bigger, the pistons, everything's bigger, because we just had to contain it. Well, we're doing better now. We're getting a lot better in designing and managing that. And we're getting them smaller, more efficient, lighter weight, better materials, all that good stuff. And diesel's really making a comeback. So it's kind of interesting. One more thing. There is another measure that we use sometimes. It's called MEP, or mean effective pressure. Okay? And basically what it is, it's the work that you get out divided by the volume change, your total volume change, or per cylinder, it doesn't really matter. Your net work divided by your volume change, which is V max divided by V min.
So it's just kind of like the average pressure.
It's kind of like an average pressure, but it really is mean effective pressure. Mean effective pressure. Mean effective pressure. It's basically a measurement of the efficiency of the cylinder, how much work you're getting out divided by the displacement. Obviously, if you have more displacement, you should get more work. So, but if you divide that out, you're basically giving an idea of its efficiency. It's just another measure. Okay?